Hi, thanks for the nice introduction. Yep, I'm Jenny Coulter. I'm from Harvard University, where I'm working in the Materials Intelligence Research Group with Professor Boris Kaczynski. Over the course of this talk, I'm going to discuss our recently developed code package called Phoebe, which is for the prediction of electron and phonon transport from first principles. So I think I don't have to convince everyone that we should be interested in understanding the transport properties of materials. When I say transport properties, I mean something a little bit different than what was discussed in the last talk. I'm talking about things like the electrical conductivity of a bulk material when we apply an electric field, or the thermal conductivity when we apply a thermal gradient. And additionally, thermoelectric effects where we see a potential difference because of an applied thermal gradient. The goal of my work is to come up with ways to accurately predict these kinds of transport properties from first principles for bulk materials. So how do we go about making these kinds of predictions? We have to think about how microscopic particle scale information can be used to predict the macroscopic scale transport effects that we're interested in. Not a question. Okay. So we have to think about the properties of electrons and phonons in the system, where when I say phonon, I mean a particle which is basically a quantization of vibration in the crystal lattice. However, it is much more complicated than this simple picture of going from microscopic to macroscopic scale information, because there are a lot of things that go into how transport plays out in a material. So these are things that we have to consider, like we have to consider simultaneously a number of different scattering processes between these electron and phonon particles. So these can be scattering processes between the same kinds of particles. So phonons scattering with phonons, or the particles scattering with each other in the electron-phonon interaction, as well as ways that these particles interact with their environment through things like boundary or defect or isotope scattering. Additionally, there are some cases where we'll see sort of exotic transport effects that will require special attention and special theory to understand them. So these are situations like the sometimes talked about hydrodynamic electron or phonon transport effects. And additionally, these calculations can be really computationally demanding for a number of reasons. So we really have to keep the performance of the codes we use to do these kinds of calculations in perspective. In order to deal with these kinds of challenges in predicting transport properties, we wrote a new code package, which we've called Phoebe. The package is named Phoebe because it is a package offering solvers for both phonon and electron Boltzmann transport equations. And we do this by including a number of different particle coupling matrix elements and also scattering rates for both electrons and phonons. And this enables us to predict a really wide range of transport effects. In addition, we've done this in a way where we've really focused on making sure that the package is high performance computing ready, so it can run and scale properly on supercomputing resources. To briefly overview what I'm going to say about Phoebe in this talk, I first need to set up the Boltzmann transport equation in a format which is numerically tractable, so sort of set up the problem which is at the heart of the Phoebe package. And then I need to talk about the kinds of functionality that we have available right now in terms of scattering rate calculations, and then from the Boltzmann transport equation solutions. Finally, because I've promised that it's got great computational performance, I'm going to show a benchmark which demonstrates this. And then I will sort of wrap up and describe the features which are available to users in the first release of Phoebe. So starting with some background on the Boltzmann transport equation as a numerical problem. When we want to set up the Boltzmann transport equation, we have to think about what happens microscopically to particles when we apply a field like an electric field or a thermal gradient. So the kinds of things we have to worry about are forces that the particles experience due to things like the electric field, diffusion of the particles across a sample due to an applied thermal gradient, or most importantly, perhaps the scattering of particles, which sort of interrupts their forward movement through the sample due to the force and diffusion terms. And we put this together in an equation where the The effects on individual particles are described through this particle population vector, which we deem F. And this is sort of the generic Boltzmann transport equation that you would see in many textbooks. So in order to solve the Boltzmann transport equation numerically, we first consider the point where the system has reached equilibrium. And then we linearize the Boltzmann transport equation by expanding this quantity F to first order. Once we've done this, now it's a linear problem, so we can arrange it into a linear algebra matrix equation type problem, where we take the components from the force and diffusion terms and put them into this vector B. And we take the scattering rate calculations that we're going to do to describe interparticle collisions, and we put them together into this scattering matrix, which I'm naming A. Since I'm going to talk about solving both phonon and electron Boltzmann transport equations, I'm noting that this is a generic equation where this new quantity labeling the indices is actually a combined state index. So for electrons, this would be like a wave vector and band index. And for phonons, it would be a Q point and phonon mode index. Once we've set up the equation in this way, we can see that what we're looking for is this solution vector, which describes the out of equilibrium particle distributions, and which once we have it, we can find the transport coefficients fairly easily. So the whole crux of the problem is looking for a way to construct this equation and solve for delta F. So then, having set up that problem, we can see that the challenge here is to actually set up this scattering matrix. When I say the scattering matrix, what I mean is a matrix where the elements represent the probability of scattering from some initial state nu to some final state nu prime. The diagonal elements of the scattering matrix represent what we would call out scattering out of some state nu. And these elements are often referred to as relaxation times, which is helpful to know because it can connect back to things that are commonly taught in classes like the Drude model. This is the key expense of the transport calculations that we do in Phoebe. And in part, it's quite expensive because the number of states needed to construct the scattering matrix and properly describe transport calculations can be quite large. So this means that the matrix is really possibly very large and takes up a tremendous amount of memory. However, we can sort of manage the cost of the calculation by initially filtering out states which are not important to transport. And this is something we do in Phoebe to kind of manage the cost of the scattering matrix. And additionally, we can make sure to treat this in a way which is memory distributed in parallel, which is something I'll talk about later. When we are constructing the scattering matrix and we want to calculate these matrix elements that tell us about scattering rates, I'm focusing on two kinds of interactions in the current release of Phoebe. So these are the electron-phonon interaction and the interaction between phonons with themselves. We can get information about how these particles couple from either density functional theory or, in the phonon case, sometimes molecular dynamics. And the pieces of information we need to understand their scattering are the electron-phonon coupling matrix elements or the anharmonic coupling constants in the case of phonon interactions. So the kinds of scattering processes we want to describe with these coupling matrix elements are going to be things like a phonon which decays into two lower energy phonons. So this is a pretty simple process that we can describe using what's called Fermi's golden rule. This expression is a little bit long, but it's very simple to understand. And basically any scattering process we're going to look at will be in this format. It's going to require some kind of coupling matrix element. In this phonon-phonon case, the anharmonic coupling matrix elements. Some occupation factors, which tell us whether or not there is a initial particle state available to scatter and some final state available to scatter into. And then energy and momentum conserving delta functions, which just enforce these conservation rules. In Phoebe, what we have to do in order to perform this calculation is use either Wannier or Fourier interpolation to transform from the matrix elements, the coupling matrix elements we get from density functional theory, to the dense mesh of state points that we need to fill in the entire scattering matrix. Because this interpolation procedure happens for each state individually, it can be really well GPU accelerated. So this is something we've done to kind of mitigate the computational cost of these transport calculations. And additionally, we've designed Phoebe to be in a way so that adding more scattering processes of this format is really simple. So that's something we hope to do and hope to offer the community going forward. Once we have set up scattering processes in this way, in Phoebe, we currently offer several different scattering rates. So for the electron, phonon, and electronic transport case, this would be just electron phonon scattering. And for the phonon phonon case, the key processes we offer are phonon phonon and phonon electron scattering. Additionally, we offer boundary and isotope scattering, but these are a little less involved to calculate, so I'm not focusing on them right now. The kinds of transport calculations we can do from scattering rates are interesting, and of course the key goal of Phoebe, but we also have interesting information at this intermediate stage. So when we calculate the scattering rates, we can also plot things like I have here, where I'm showing the band structure of gallium nitride with the electron phonon line was projected onto the band structure. So we can also get things like this out of Phoebe, which can help us understand the eventual transport calculations that we compute. Once we have the scattering rates, we can sort of sum over the processes that contribute to scattering in and out of each state, and we can construct the full scattering matrix. We can return to the matrix equation that I set up earlier in the talk, and now we can focus on solving for this delta F out of equilibrium population vector. So then I have to go into the functionality that Phoebe offers in terms of solving the Boltzmann transport equation. So to solve the Boltzmann transport equation, Phoebe offers a range of different solvers that span sort of this spectrum of cost and accuracy trade-off. There are different solvers which would be appropriate for different situations, but one of the most commonly used ones, which is applicable and appropriate in many situations, is the commonly known relaxation time approximation. So this is a process where we basically pretend the off-diagonal elements of the scattering matrix are not important, and we consider just the lifetimes along the diagonal of the scattering matrix. This means, of course, that the solution to the linear algebra problem is trivial. And we can get a pretty good answer for most materials. However, there are some materials where these off-diagonal elements are really important, and we need to consider a relatively strong, what we would call normal or momentum conserving scattering processes. And in these cases, the RTA can fail. So for such a case, we offer what are called a few of what we call exact PTE solvers, where we use the entire scattering matrix in the calculation. And so the first of these that we offer are the two kinds of iterative solvers, one which we just call a simple iterative solver, which really is very straightforward. And then a second one, which is a variational solver for cases where the convergence of the simple iterative solver might be a bit poor. And both of these use the full scattering matrix formalism in the calculation and therefore produce more accurate results, especially in the cases where normal or momentum conserving scattering is very important. So we can show an example of how these calculations work out in practice. And here we have an example calculation using the thermoelectric material cobalt antimonide. I have calculations from Phoebe for the lattice thermal conductivity, electrical conductivity, and Seebeck coefficient. Where here we have used both the RTA and simple iterative solvers to compare to experimental values for these transport coefficients. So we can see first that we have pretty nice agreement with the experiment, which is always very exciting. But additionally, we can see that in this case, the RTA and iterative solvers are also in pretty good agreement, indicating that the RTA was an appropriate approximation to use here. However, there are some other cases. For example, here we can see in black phosphorus that comparing the RTA and variational solvers, the exact solution of the Boltzmann transport equation was very necessary. And this is in part because this is one of the situations that I mentioned on the first slide, sort of a potentially exotic transport effect, where hydrodynamic phonon transport has been observed in experiment for black phosphorus. So this is the kind of case where we actually do need these specialized solvers that Phoebe offers. Additionally, we have one more very specialized and somewhat expensive solver for specifically hydrodynamic situations again. This is another one of our exact PTE solvers, but in this case, we approach the matrix equation problem through basically a direct diagonalization of the scattering matrix, which is, of course, why it's so expensive. However, you get some additional information that the iterative and variational solvers would not have provided. So in this case, you would get lifetimes and eigenmodes for collective excitations that describe transport in one of these hydrodynamic systems. So sometimes when you want to do an analysis of this kind of transport regime, this additional information can be important and necessary. Finally, we have one more of the approximate methods. This one is, again, pretty specialized. It only applies to electronic transport driven by electron-phonon scattering. It works by taking electron-phonon matrix elements from density functional theory. And instead of going to this Wannier interpolation step, which can be somewhat expensive, we skip that and we take a momentum average of the electron-phonon matrix elements from density functional theory and use that in a different way instead. This is handy because since we don't have to do the interpolation, we can skip the step of Wannierizing the band structure, and means that the cost of the electron-phonon average approximation calculation is only the cost of a phonon calculation from density functional theory. This makes it also very easy to automate because now many databases are starting to have phonon calculations included. However, it is still a little bit approximate, so we have to be aware of that. And to show how this approximation works in practice, I have here two examples of different 2D materials using both the RTA method that I mentioned first and the EPA method here in gray for comparison of the electron-phonon lifetimes. Here we can see that there's a fairly nice agreement for most of the energy range of the band structure of these materials, which is really nice given how computationally less demanding this method is. Okay. So now, because I have promised that this package is also a sort of high performance package, I definitely owe you a few benchmarks to back up these claims. We've written Phoebe to be extremely parallel. So we've used both OpenMP and MPI hybrid parallelism, as well as parallel read-write of large files through HDF5. We're performing a lot of these memory distributed linear algebra operations of the scattering matrix using Scalapack. And we also provide a pretty extensive GPU acceleration using the COCOS package. And this, like I mentioned earlier, helps us get over the cost of this scattering matrix calculation. Additionally, we have written this code in object-oriented C++ with the aim of making it easy to add new transport effects and scattering rates. And we've left it open source on GitHub because we want people to do this, and we want to hear feedback from users about what they'd like to see in the code package in the future. To demonstrate, for example, the GPU acceleration of the code, I have a benchmark of our GPU versus CPU performance. So we're taking gallium nitride, which is a pretty standard transport calculation, in this case, a fairly well-converged transport calculation mesh using our iterative solver. And we're comparing 4 MPI processes with each access to 8 OpenMP threads to 4 V100 GPUs. We can see, of course, that the read-write of files is about the same, but there is a tremendous acceleration of the initial calculation of basic phonon properties in the code, a little bit of boost for the electronic transport properties, but a tremendous effect on the calculation of the scattering rate, where we see about a 20 times speed up on the scattering matrix calculation, which translates into an overall about order of magnitude speed up on the total calculation time when using GPUs. So we actually have really effectively accelerated the calculation with GPUs, and this gives us the electrical transport of gallium nitride in about a minute. So that's really quite nice in terms of what is available from other code packages right now. Additionally, when claiming this is high performance, yes, it should also scale really well on large supercomputing platforms. So taking a slightly more dense gallium nitride calculation, we can see and demonstrate that for the calculation of the scattering matrix, which is here in the dashed lines of this calculation, both with and without GPUs, we see that this calculation of the scattering matrix, the most expensive part of the calculation, follows ideal scaling in both the more CPU-oriented case as well as up to 64 GPU nodes. So this is something we're really excited about. And this means that we can go ahead and perform calculations, which would be rather larger than ones that were available in the past. So just to summarize the contents of the first version of Phoebe for anyone who might be potentially interested in using it, at sort of the user level, what we offer is we can take electron phonon or phonon coupling information from a couple different packages. So for electronic transport, we use the DFT code Quantum Espresso to take electron phonon information. For phonon transport, we can take information from PhonoPy, ShankBT, or molecular dynamics calculations through LAMMPS. When we want to calculate scattering rates to fill in the scattering matrix, we're offering electron phonon, phonon electron, phonon isotope, and boundary scattering rates, which can all be optionally added into the scattering matrix through flags in the input file. And then finally, we can choose from a range of different solvers when we want to actually solve the Boltzmann transport equation and gain transport coefficients. So I've demonstrated all of these, but a few things that we think about going forward. We've written Phoebe to be very easy to take inputs from other code packages. So say in the future, maybe VASP will release electron phonon matrix elements. Perhaps we could add in new features in that direction. And additionally, because we have structured the code packages in a way which makes it easy to add new scattering processes, we can think about things like electron-electron scattering, or perhaps the effect of a magnetic field on scattering rates as well. And we're very open to hearing from users about what kinds of features they would like in terms especially of new scattering rates. I guess the summary of that is that you should stay tuned for future developments or reach out to us if there's something you'd really like to see. Before going to any questions anyone might have, I need to thank the rest of the Phoebe team because, of course, I did not write this whole package all on my own. I first have to thank Andrea Cepolati, who was a research scientist on this project and is now at Microsoft Research. He had a tremendous leadership role in this project. I also have to thank Anders Johansson, who is one of the people who worked tremendously on the GPU acceleration of the code. Natalia Fedorova for helping us with the electron phonon average approximation of implementation. And then, of course, my advisor, Boris Kaczynski, who was a tremendous guiding hand in terms of the direction of this project. So with that, I can answer any questions that anyone might have.